Today we're going to talk about section 5.2 again. This is the second part of our numerical integration discussion. So as we saw last week with the numerical integration methods, there are several that we can use to do so. Last class we talked about the Trapezoidal Rule and Simpsons Rule over just one interval. So here we're going to talk about what are called composite Newton-Cotes formulas. So let's look at the definition of those. The definition of a composite Newton-Cotes formula, basically these composite formulas just divide the area under f of x on the interval a to b into smaller subintervals called panels. And we sum all of the approximations for those panels to get the overall area approximation for f. Okay, so we have we'll deal with two composite rules at the moment. The first is the composite trapezoidal rule. You can see here that the integral from a to b of f is this guy here. So it kind of mirrors the trapezoidal rule we saw last class, except it has this big summation right here. And the error term looks a little bit different. So let's take some time to develop this formula. We'll do this geometrically, and then we'll see how it plays out. Okay, so let's consider that we have this function here, let's say. So recall that the trapezoidal rule, let's say we have from A to B here. Remember that the trapezoidal rule approximated the area under this curve from A to B using just one trapezoid, right? So we would have this kind of trapezoid here, right? We're using the line as our interpolant for the function. And then we're calculating the area just using a formula for trapezoids, basically, for this guy here. However, we can see that there's a big error in the actual approximation here because all of this area is not underneath the curve. So we're going to have a pretty terrible approximation if we just use one big interval. Okay, we could, using these composite formulas, actually you can get a better approximation. Basically what we're going to do is just break this interval up into smaller subintervals and use smaller trapezoids to approximate that area. Okay, so first thing I'm going to do is just partition this axis into equal subintervals. So I'm going to call this x naught here. And then I'm going to say next x, let's say, is x1, and then x2, and x3, and so on. Let's call this guy xm, okay? So the one right before that would be xm minus 1. And the one right before that would be xm minus 2. Okay? And I've partitioned this so that all of these distances between all of those x coordinates are the same. And I'm going to call this distance h in every case, right? So this distance here is h. That's h. Here we have h. Here we have h. Okay? So it's just the difference in the coordinates, like our delta x, basically. Okay? So what we're going to do here is use smaller interpolating polynomials, smaller sections of these lines to generate different trapezoids, right? So instead of using this one giant trapezoid from the endpoints of the interval I'm looking for, I'm going to create trapezoids in between each and every one of these subintervals, right? So do the same kind of thinking with this. So use these 2 points for the first subinterval to generate some trapezoid like this. Okay. Then I'll do it again. So I'll use these 2 points to generate another trapezoid. And again here. And again here. And here again. Okay? And we'll do that for all the x's in between as well. Okay? So, you can see here that when we do this composite method, our error is a little bit, because these don't really match up perfectly to the curve because they are lines. But you can see as we have this composite method, the error is much, much lower. We have a better approximation to the actual integral of this thing. Okay? So let's think about this geometrically. How do we calculate the area of each of these trapezoids? Well, we know that the integral from a to b of f of x dx will be equal to, okay, so we're going to use equality here because we're going to account for the error terms for each of these trapezoids. So the integral from a to b of f of x dx is equal to the areas of all of these trapezoids plus their error terms combined, right? So let's look at the first one. The first area here will be, to calculate the area of a trapezoid, we do the width times the average of the two lengths here, the two parallel sides. So that would be h over 2 times, now what are these values here? Well, that's just y0 and y1, right? y0 and y1. Okay. y0 plus y1. Okay. And of course, from the trapezoidal rule from last class, we can look at the error term for each. The error term here would be minus h to the third power over 12 times f double prime at some value of c in between x1 and x0. So let's call that c1. Okay. So this accounts for that first area plus the error term that we're dealing with there too. Okay. Then we need to add the second panel here, the area of the second panel, which is similar in process, right? So h over 2 times the y-coordinate at x2 plus the y-coordinate at x1, so 1 plus y2. Minus the error term, which is the same thing, except at a different value of c, let's say c2. c2 would be the in-between x1 and x2 here. Okay. And the next panel, you guessed it, h over 2 times y2 plus y3 minus h cubed over 12 f double prime of c3. Of course, we would continue that on and on for all the various panels that we have. So we'll do dot, dot, dot. And the last two panels, so let's look at those. This last panel here would be h over 2 times y at m minus 2 plus y at m minus 1 minus the error at, let's say, c m minus 1. And then finally, our last one will be h over 2, y m, this should be a m minus 2, by the way, m minus 2. Y m minus 1 plus 1 m minus h cubed over 12, f double prime of c m. So this is the sum of all of those panels, which gives us, and the error terms accounted for, so it gives us the value of this integral exactly. Okay. So let's take a look at the how we can kind of simplify this a little bit. Okay. So if you notice, every term here has an h over 2 for these guys in this column here. And we have every term here has h cubed over 12 times the second derivative at some value. So what we can do is kind of re-represent both of these as summations, right? So this is equivalent 2. So let's look at this here. So note we have some patterns evolving here. So note that for the first one, everybody has h over 2, so we can say h over 2. Also note that we have repeating y terms in each successive calculation, right? So y naught, there is only one y naught here, right? So let's say if I factored out all the h over 2's, I would have y naught plus y1 plus y1 plus y2 plus y2 plus y3 plus y3, so on and so forth. So you can see all of those intermediate points that are within the interval always show up twice because it's an endpoint for the first interval and the second interval. So we have two values of y1 happening there, right? So if I were to write this entire thing out by factoring out h over 2, I would get y naught plus y1 plus y1, that would be 2 y1s, plus 2 y2s, and so on. And it would stop being multiplied by 2 once we got to the very last one. We would have x, the y-coordinate for x sub m minus 1 would be accounted for in both of these trapezoids. So the very last one would be 2m minus 1 plus ym minus, all of these can be written as a summation straight away, so that would be h cubed over 12 times the summation as I goes from 1 to looks like m of f double prime of c of I. So. All right, if we notice here, we have some commonality in the center terms, right? So we only have one y naught and one ym. So we can rewrite this like this. I'm going to put my y naught here, I'm going to take my ym, put him over top here. And then all the center ones are multiplied by 2. So that would be 2 times the sum of all of those y's. So sigma I goes from 1 to m minus 1 yi minus, actually I'm going to put this back inside here. So sigma I equals 1 to m h cubed over 12 f double prime at ci. Okay. So you can see basically we have the this portion of our formula, right? This portion of our formula is here, right? But we need to kind of manipulate the error term to get it into a more usable form, right? So how do we do that? Well, let's look. We can use a theorem. So by Theorem 5.1, that's in your book. This is basically the generalized intermediate value theorem. We used this theorem when we did when we started talking about numerical differentiation. So let's take a look at that theorem. Here it is. So the generalized intermediate value theorem says let f be a continuous function on the interval a to b, let x1 through xn be points in a to b, and a1 through an be positive. Then there exists a number c between a and b such that this relationship is true, right? So if we notice, it's the sum of all of these constants times some function values along our interval, right? As long as the conditions are met, that is, f is continuous on a to b, and these a's are positive, then we can actually rewrite that as the sum of all the a terms times the function evaluated at some c, where c is a number between x1 and xn, okay? So we can actually utilize that formula here. Here's why. So if you notice, go back. If you notice here, notice that this is the sum of all of some number multiplied by some function evaluated at these c's, which are in between a and b, right? So basically that's what this side of the problem is. Even though our a1s are like h cubed over 12, they're all h cubed over 12. And our functions are the second derivative instead of just f. But basically it fits this form. It's the sum of a bunch of constant multiples of the function at different values of c, which are within our interval a to b. Okay? So all of these are satisfied. F is continuous on the interval. All of our c's, our c1s through cn's, are points within a and b. And all of our terms in front, h cubed over 12, they're all positive because h is positive. That means that we can write this right-hand side like this. So it's the sum of all of the coefficients, which are our h cubed over 12s, times the function evaluated at some other c within the interval. So what we can do is rewrite the error term so just rewriting this guy here. We can actually rewrite this error term as something being multiplied, so it would be h cubed over 12 plus h cubed over 12 plus h cubed over 12 times f double prime at some other c value, right? So that's basically what this is, the side of the equation that we're utilizing. All of our coefficients are h cubed over 12s, and then we evaluate the function, which is the second derivative at some other c value here. So if we take a look at this sum, we are adding h to the third over 12 a bunch of times. How many times are we adding it? Well, that would be the number of panels that we have, right? In this case, it would be m times, right? So we can actually rewrite this as h cubed over 12 times m times f double prime at c. Again, we're adding h cubed over 12 m times. So we have m panels. Okay. So lastly, we can actually manipulate this term just a little bit to make it to what we want it to be. So if we go back to our notes, we need to get this b minus a h squared in there. So something must happen with h cubed times m. Well, let's think about it. Here, what is h times m? What is h times m? Well, if we look back, h is simply the length of each of these intervals, right? So I have this length, this length, this length, this length, this length here, right? They're all the same. And we have m of them, right? So if I multiply h times m, I simply get the length of this interval right here, right? Therefore, h times m is simply the length of the interval b minus a, which implies that m is equal to b minus a over h. Therefore, we can conclude our derivation of the trapezoidal rule by just inputting this b minus a over h, right? So finally, so if I put in b minus a over h here, one of these h's is going to cancel. So I get my b minus a over 12 h squared times f double prime at c. That's exactly what we wanted here. Okay? Now, composite Simpson rule is derived in a similar fashion. We'll utilize them in a second. I just want to derive these formulas first for you. So here we have the composite Simpson's rule, which looks similar to that of our Simpson's rule over just one interval. So you can see kind of the coefficients match up. You just have these summations, and the error term is a little bit different. So let's look at composite Simpson's rule. We'll do the same kind of thing. We'll do a graphic interpretation. So remember that Simpson's rule was different from Trapezoidal rule because instead of using lines as our interpolating polynomials, we used quadratic curves, parabolas, as our as our interpolating polynomials, that is. So if we look here, same function. So we have our functions. Okay. On A to B. Composite Simpson's rule over just one interval, use just one parabola with an extra point in the middle to help determine the area under the curve. We saw that it was a bit better for our example that we did. But composite Simpson's rule uses many pieces of the quadratic function to do so, right? So what we do, let's say we want to have 3 panels, right? If we want to have 3 panels, so let's say M is 3 panels here. Basically, in order to interpolate that, the first panel needs to have 3 points, right? Because our interpolating polynomial must have of degree n, n minus 1 is determined by the number of points minus 1. So in the first panel, if we're using a quadratic, we need to go up to x2 and use x1, right? So again, we have to have 3 points in order to fit a parabola to this section of the graph, okay? So the parabola would interpolate this portion of the curve, right? And then we would find, using our Simpson's rule formula, this value of this area, right, approximately. The next panel, so we're going to go for 3 panels here. We'll split this A to B up into 3 equal portions. Would go up to x4, right? And x3 we would use. So we would use these 3 points at x2, at x3, and at x4 to fit some sort of quadratic portion to that piece of the curve. And then use the Simpson's rule formula to calculate this area. Therefore, B, if we were doing 3 panels, the last panel would end at x6, right? x6. And would use x5 as another point to interpolate at, right? So we have these points. We would fit some quadratic to them. Okay? And find the area under this panel. Okay? So here, notice that the number of panels is not, the number of x values will increase, right? So in the trapezoidal rule, we had m panels. Here's our trapezoidal rule example again. We had m panels. In this case, we had m panels with m x's, right? With this Simpson's rule, it doubles that, right? So we have 3 panels, but we have 6 x's, right? So I'm going to generalize that breakdown. So let's do it one more time. So let's say we're going from A to B, right? And let's call this guy x0. Now B is going to be twice the number of panels. So I'm going to the x value, there will be twice as many x values as we have in the trapezoidal rule, because the interpolation uses more points per panel, right? So here the first panel would go up to x2 and use x1, right? Again, we would use these points along the curve, fit a interpolate a quadratic to them, find this area here. The next one would go up to 4, right? Use x3 and use these points to interpolate, right? Now at the very end, that we would use this point and the 2 previous points to get the very last panel. So the one right before that would be x of 2m minus 1, and the one before that would be x of 2m minus 2. We'll be using these 3 points and some quadratic to approximate that area, and then everything in between, right? So we can generalize the integral just like we did with our trapezoidal rule, okay, using our Simpsons rule formula for each. Okay, so the integral from a to b of f of x dx is equal to the sum of all of these areas and the area terms, right? So if we look back at your Simpsons rule formula, to get the area of this guy, it's going to be equivalent to h over 3 times y naught plus 4y1 plus y2. Okay. Minus the area term, which would be h to the 5th over 90 f the 4th derivative of f at, let's say, c1. So that gives us the area of the first panel. For the second panel, same idea. So we're going to add h over 3 times. Now, this panel uses x2, x3, and x4, or the y coordinates at those points. So y2 plus 4y3 plus y4. Minus the error term there, h to the 5th over 90, f quadruple prime of c2, let's say. Okay. So you can see that if we repeat that process, the very last panel that we have will be h over 3. Y sub 2m minus 2 plus y sub 2m minus 4 y sub 2m minus 1 plus y sub 2m minus the error term there, which would be h to the 5th over 90 f quadruple prime of c. Now let's just match up the subscripts here. We said that this was C1, C2. Let's call this, let's call this C naught actually. Okay, C naught matches to this, C2 matches to that. So this would be C2m minus 2. Just to fit the pattern so that we can write this as a summation. Okay. All right. So now if we look, we can try to condense this into a more simple format here. So let's look at the patterns that we see in these terms here. So know that y naught only appears one time, right? It does not appear in any other values here. So I'm going to factor off the h cubes from all of these terms, and then we'll see what we get, right? So let's see, we'll have y naught plus, how many y1s will we have overall? Well, just these 4, right? 4 y1s plus how many y2s altogether? Here we have a y2, here we have a y2, so 2 y2s plus 4 y3s plus how many y4s will we have? We'll have 2 of those as well, because in the next term we're going to have that same kind of pattern. So 2 y4s, and then 4 y5s, plus dot dot dot, come down the line here. Let's think about how many of these we're going to have. Well, if we continue the pattern, we're going to have 2 y sub 2m minus 2s, 4 y sub 2m minus 1s, and then how many y sub 2m's will we have? Well, just 1, because that's our last term. So plus y sub 2m there, minus our error term, which is the summation, let's say, the summation of all of these guys. So that would be h to the 5th of 90, f quadruple prime of c I, and let's say, well, if we notice here, these c's have subscripts that kind of go up by 2 every time, so it's like an even number. So let's say 2i here. Alright, and then I is going to range from 0, let's say, so that would be, give us our C0 there, to 2m minus 2, so we need to go to m minus 1 from that. We can further compact this term here, okay, if we notice something. So, if we notice, the first term and the very last term are only counted once, right? So h naught plus, or excuse me, y naught plus y sub 2m are just counted once. Now, we notice that all of the odd indexed y's are all multiplied by 4, so we can actually write that as a summation. So how do we write an odd number? Well, that would be an even number minus 1, right? As I goes from, let's say, 1 to m. Okay. Plus, now all the even indexed ones that are in the center are all multiplied by 2. So this would be y sub 2i, an even number. I goes from 1 to the last one that's multiplied by 2 is 2m minus 2, so we just need to go to m minus 1 here. Minus our error term, sum I goes from 0 to m minus 1, h to the 5th over 90, times f quadruple prime at c sub 2i. So we're almost there. All we need to do is just rewrite this error term using the same kind of procedure that we did last time. Okay. So all of this is good for our formula there. So I'm just going to work with the error term and then we'll come back. Okay. So note that we are summing a bunch of terms. So by Theorem 5.1, sigma I goes from 0 to m minus 1 of h to the 5th over 90, f quadruple prime of c2i. Again, all of these c's are in between a and b. All of these h to the 5th over 90 are positive, and f is continuous on the interval. F, we're assuming that f quadruple prime is continuous. then this can be written as the sum of a bunch of h to the 5th over 90s times f quadruple prime evaluated at some other c in between all these, in between a and b, right? So how many of these do I have? How many of these do I have? Well, it depends on how many panels I have, right? So in this case, we have m panels, yes? So this would be h to the 5th over 90 times m, as we saw last time. Okay. Now let's think about quantity. So if we go back to our diagram, let's think about how we get this length, this b minus a, right? So if we go, we have m panels, right? What's the length of each of these panels? So this length along the x-axis is no longer h, right? Because we said that h was here and here. So the length of each of them is 2h, actually. We have m panels of length 2h, so the length of this interval is 2h times m. So now 2h times m is equal to b minus a, which means that m is equal to b minus a over 2h. Thus, our formula, let's say here star equals h over 3 y naught plus y sub 2m plus 4 sum 2 sum minus, now we're going to plug in our b minus a over 2h here, so that h is going to, one of those h's is going to cancel. We'll have a b minus a at the top, and then that 2 multiplies the 90, so we'll have b minus a h to the 4th over 180 times f quadruple prime at c. So here is our composite. Simpsons Rule, right? Matches exactly there, right? So all we need to do is just utilize the rule. So here we approximate the antiderivative, the integral, definite integral by this term here, and this gives us a bound on the error of the approximation. All right, so let's do an example here. See how we actually implement these formulas. So we want to carry out 4 panel approximations to the integral 1 to 2 of natural log using composite trapezoid and composite Simpsons rules, and then find upper bounds on the error of the approximations. Okay. So example 1. First we'll deal with the trapezoidal rule. Okay. So with these composite formulas, it's a good idea to partition your axis. We don't necessarily have to graph it, but we do need to know what x values we have to evaluate at, right? We have to find some y values for specific x values for our function, right? So let's see. We're subdividing the x-axis into 4 panels using the trapezoidal rule. Now recall, so we're going to have 4 trapezoids here, and we know that the trapezoidal rule only, so for every m panels we'll have m x values, so we need 4 x values here. So what would these, so we have 1 and 2 at our endpoints, but what would these 2 be? Well, that's what divides this interval into 4 equal pieces. Remember, we have to have equal distances between each of them. So it looks like the length of the interval divided by the number of panels, which would be 4 panels, right? We need 4 panels, is 2 minus 1 over 4, or 1/4. So we have 1.25, 1.5, 1.75. Okay? So you have 4 panels of equal width, right? So here are our x values that we'll use for our trapezoidal rule. Okay? So let's think back to our trapezoidal rule. It's above here. Here's our trapezoidal formula for composite trapezoid rule. So we know that the integral from 1 to 2 of the natural log of x dx can be approximated by this portion of our formula here. Okay, so it would be h over 2. And what is h here? Well, h is 1/4, right? This is equal to h. So h is 1/4. So we have 0.25 divided by 2 times y naught plus ym. Well, y naught would be the function evaluated at x naught. That's this guy here, right? This is an x naught, x1, x2, x3, x4. So it would be the natural log of 1 plus y sub m is the function evaluated at the other endpoint, which would be natural log of 2. All right. And then we have the sum of 2 times the sum of all the interior y coordinates, right? So that would be plus 2 times the sum of all the function values here, right? So that would be natural log of 1.25 plus natural log of 1.5 plus natural log of 1.75. Sorry for the space there. Okay. So let's see what we get. 0.25. Use your calculator here. 0.25 over 2 times, the natural log of 1 is 0. So we can skip that. Natural log of 2 plus 2 times the sum, natural log of 1.25 plus natural log of 1.5 plus natural log of 1.75. So here, just inputting all of that into my calculator gives 0.3837 approximately. So at 4 decimal places, we get this approximation using our trapezoidal rule. Okay. Now we need to find the error bounds, right? So the maximum error is given by negative b minus a. So just utilizing the error term there, okay? Utilizing the final error term, b minus a, h squared over 12 f double prime at c. So here we know our b and our a, we know our h, so it would be negative. B minus a is 2 minus 1. H is 0.25 squared over 12 times the second derivative at some c, and c is in between these two values, 1 and 2. So what's the second derivative of the natural log? Well, the first derivative is 1 over x. The second derivative would be negative 1 over x squared at c. Okay. So on top, let's see what we'll get. The negatives are going to cancel here. So you get 1 times 0.25 squared divided by 12. It's 1 over 192 c squared. This is 1 over 192. So which endpoint is going to provide the maximum would be the lowest of the two endpoints. So using 1, this is less than or equal to, remember c is between 1 and 2. So 1 would provide the max error, so that would be 1 over 192, or approximately 0.0052. So this is the max error for our trapezoidal rule. Now for Simpsons rule, okay. So with Simpsons rule, if you have your formula handy for that, note that we need to partition the x-axis into two x coordinates, right? So if we want, here's 1 to 2, that's our x naught. We want 4 panels, so this would be our 8th x value, okay? So if we partition that, we have x4 in the middle, x2, x1, x3, x6, and x5 and x7. So all we need to do is figure out what our h is. H will then be equal to b minus a over 2 times our number of panels we want, which is 2 minus 1 over 2 times 4 is 8. So each is an 1/8, right? 1/8 or 0.125. Okay. So here I'll have 1.125. .25, 1.375, 1.5, 1.625, 1.75, and 1.875. Okay. So the integral from 1 to 2 of the natural log of x is equal to h over 3, so 0.125 over 3 times y naught. Y naught would be the natural log of 1 plus the natural log of the last x, which is 2, natural log of 2, plus 4 times the sum of all of the odd interior terms. So the odd ones would be x1, x3, the natural log of all of these, 5 and 7, right? So the natural log of 1.125 plus the natural log of 1.375 plus natural log 1.625 plus natural log 1.875 plus 2 times the sum of all of the even interior function evaluations. So that would be natural log of 1.25, natural log of 1.5, and natural log of 1.75. Again, this is the approximation. Approximately equal to this sum. So if we do this calculation, we get approximately 0.3863 to 4 decimal places. Okay? The error term here, max error, is negative b minus a, h to the 4th over 180 times f quadruple prime at c. This will give us negative 2 minus 1, 0.125 to the 4th over 180 times the 4th derivative of the natural log is negative 6 over x to negative 6 over x to the 4th, evaluate at c, so c to the 4th. And we know that this is less than or equal to, because when c is 1, we get the maximum value for this. Let's see what we get. So the negatives will cancel. We have 0.125 to the 4th times 6 over 180. Which is 8.138 times 10 to the negative 6th power. So this is the maximum error for our Simpsons Rule method. So you can see that the error is significantly less than that of the trapezoidal rule, as we should expect. Now we're going to talk about... Now we're going to talk about open Newton-Cotes methods. We require these methods when we are dealing with a function that has discontinuity at the endpoints of the a-b interval or within the interval that we are approximating the integral for. So one of those methods is called the Midpoint Rule, which is given here. I'm not going to go through the proof of that, but I will show you where it comes from. So midpoint rule, basically if we have our function, a to b, let's say, or if we're dealing with one interval. Basically what we're going to do, let's say we have a discontinuity at this endpoint here. If we have this discontinuity, or at both endpoints for that matter, let's say we have this removable discontinuity right here. We could have an asymptote there as well. There's no way to get the function value for f of x naught or y naught. So what we do is we utilize the midpoint of this interval. So here, the midpoint of this guy is going to be x naught plus h over 2. Okay? So again, the entire length of this interval is h. So adding x naught plus half of h gives us this coordinate here. Then we utilize a rectangle to generate the area approximation for our method. Okay, so the integral from x naught to x1 of f of x dx will be the length of this rectangle h times the height of the rectangle, which is f of this value here, f of x naught plus h over 2, plus some error term. It ends up that the error for our midpoint method is h cubed over 24 times f double prime at c. Okay? We can actually write this as h times f of w if we redefine w as that midpoint. Where w equals x naught plus h over 2. Okay. So we see that this midpoint rule gives us a pretty good error term for our approximation. We can also extend that to a composite rule by doing a similar thing that what we did last time, right? So instead we have this function we partition the axis like so. Let's say this is x sub m. Here's x1, x2, xm minus 1, and so forth. We can generate the midpoint approximations by using rectangles extending between all of our midpoints here. Of course, we would sum all of the areas here for our composite midpoint rule. Again, we're using the midpoints of all of these intervals, summing them up. That will yield the formula that we have right here. Okay. So let's apply the composite midpoint rule with 4 panels to approximate the solution to this definite integral right here. Okay. So if we take a look at the graph of this thing in our calculator, let's look at e to the x minus 1 over x. And we'll sort of 6 it. All right, so we're just looking at the So we're looking at this interval right here, 0 to 1. So let's graph that. Also note that a discontinuity occurs at x equal to 0. In fact, that is a removable discontinuity. So when we have our graph, we have a hole at 0, and then the curve extends to this point 1. 0 to 1. So if we're going to use the midpoint rule, we just partition this into however many panels that we want, right? So here we want 4 panels for this composite rule. Right? So h would be b minus a over m this time. 1 minus 0 over 4 is a fourth. So h is a fourth, 0.25, 0.5, and 0.75. So we have these four, we have partitioned the axis into four pieces. Now what we want to do is use the midpoint of each of these intervals to make a rectangle to approximate the value of the integral. Something like that. So we need these midpoint values in our calculation. So here, what would the midpoint value be between 0 and 0.25? Well, W1, let's say, midpoint would be 0.25 plus 0 over 2, just the average, which is 0.125. So here we have 0.125. Midpoint 2 would be 0.5 plus 0.25 over 2, just the average of those. Which is 0.375. Here we would have 0.625, and here 0.875. And so these are all the midpoints. This is example 2. So apply the composite midpoint rule to approximate the solution. So we're just using this formula here. Therefore, the integral from 0 to 1 of e to the x minus e to the x minus 1 over x is equal to h, which is 1/4 times the sum of all function values evaluated at these midpoints here. So e to the 0.125 minus 1 over 0.125 plus e to the 0.375 minus 1 over 0.375 plus e to the 0.625 minus 1 over 0.625. Of course, this is an approximation, right? Approximately equal to plus e to the 0.875 minus 1 over 0.875, which equals approximately 1.3166. Alright, so here is the approximate solution to our integral. Alright, so you can now take a look at the section 5.2 exercises number 1, 4, and 6. Just do part A only for each of those. There runs you through the trapezoid method for 1, Simpsons Rule for 4, and then Midpoint Rule for 6. Just do part A there. And then computer problems 3, 4, and 5. Again, trapezoid, Simpson, Midpoint. If you have any questions, just feel free to email them to me. You can also set up a Google Meet time with me to talk about a problem you're having if you need to. Just email me your availability on those.